players and the movements of the players are very can take input is what I'm trying kind of saying, like from many different variables around the map, and a lot of information that the players either get from the game itself or that have already realized themselves. Still, like my hypothesis is basically that the spatial temporal data itself, so the positions and the timestamps of those positions would hold enough kind of information to make some sort of meaningful predictions about the movements of the players. So that's what I'm kind of looking to do. So in context of this game, but perhaps in other complex games as this as well, like to kind of show that perhaps it's possible to reduce features significantly for some scenarios and just use, for example, the positional data of the players. I have some tiny amount of code and some some very simple models also created. This here is just an animation for kind of showing the results of the models. This doesn't have the model results, so the green dot is the actual H time step up ahead result, and the blue dots are the previous results, the history that would be fed to the model, and then the model would place another dot in here, but that's unfortunately not shown in the animation. And alongside kind of those sort of visual verification, we can create some. Can I make this any smarter? We can create plots for different models for their accuracy. This one's just a linear regression model that shows that, yeah, if we have a small amount of just a small amount of history being fed to the model, and like a varied amount of time steps ahead that is being predicted, it doesn't matter. It's basically the same. It doesn't do very well. It does do better when the time step at the look ahead length is smaller, but it doesn't change much. And then I have just some example models, like a random step in a random direction, just taking the last position instead of predicting anything new, and then just picking a random spot on the map as a model. Which, well, I mean, already from these we could probably also already see that, like, the random position model has a RMSE of about 5,500, which at least is something that linear model beats. So hey, but this I actually, this one is rather for my this code that I'm doing right now is for my machine learning project, but what I'm looking to do for my thesis is doing some more complex model, like a graph based neural network, to really kind of dive into the fact that there are very complex rules within the game that should be encoded in many ways in just positional data of the players. So that's mostly what I have at this point.
Very interesting project, Inmari. So my first question would be, does anybody know what my first question would be? Okay, so I'm not 100% redundant already, which is good. So what is a data point in your application? How would you call the data point in this case?
The data point would have to be a vector of a vector that contains all the positions of all the players at a given timestamp. So
okay,
so yeah,
this would actually be vectors. this would actually be what I would call a feature. So a feature is a part, it's like one
Yeah.
perspective on the data point, but the data point might be much, much more complicated. A data point could be a certain state or at a certain time instant of a game.
Yeah. Yes.
And then
Sure.
you not only have the short-term history of the players or the pixels in the video or in the rendering, but you know even the manufacturer of the game, any info from the Wikipedia entry for that game. This could all be features. So, and this you could all feed into a big nonlinear model, a neural network. And it seems you have already managed to extract some features and fit a linear model. So I mean, now you go from there. So you try out maybe the same features using a nonlinear model, a neural network, or
Yeah.
also using different features. So not only, so as I understand, currently you use the short-term history of player locations or positions.
And just like just a single player. So
Single player.
so even though the one player is like playing the game with 9 other players, we're just currently just disregarding all the other player movements,
Yeah.
which
Yeah.
is not realistic. But yeah.
Very good. And then so a basic recipe for implementing the machine learning could be first try to get the training error 0. So on the time instance where you train the model, try to really get low RMSE, essentially 0. Even when you overfit, so you of course
Yeah.
need to
Okay.
evaluate the trained model then on another game, for example, or at future time instance which you didn't use to tune the model. So you need to do some validation, and this validation error might be high in the beginning. But the first step should be get the training error to 0, even overfitting, and then work backwards. So try to regularize the model to reduce the validation error, even at the expense of increasing a bit the training error. And at some sweet spot, these two errors meet. And then if you're lucky, training error is on the same level as validation error and on the same level as the required accuracy, you're done. But this, to find out if you're done, requires that you know a baseline. So do you have reference values for RMSE where you would say, okay, this RMSE value is quite good. There's not much hope for better.
No, there's not really other models like
Yeah,
this.
yeah,
There's a few different reasons, I guess,
yeah.
but for example, the data itself is a bit hard to get on this game. But I actually, now I'm thinking that I haven't looked into other games that I think have a bit better data available, for example, that could have something. Maybe I
Yeah.
could find some sort of reference value like that, because there are similar genre of games as this.
So in general, does anyone know how we could get the baseline for saying that, okay, I now have find a model, so this is a trained model or hypothesis, trained model, and it predicts the label, like the future positions of the players, and it has some error. Let's say y hat minus the true label is squared is 0.1. How do we know if this value is good or bad? Where can we get a baseline from? Any comments from the audience?
Wouldn't it depend on the assumptions on your error distribution?
Yeah, so I heard already some trigger words, distribution. So that's one of the cool things you can do with probability theory. You can not only torture students with probability theory, but you can get baselines. So if you have a joint distribution of features and labels, then you can evaluate using basic calculations the posterior distribution of the label given the features. And this distribution might look like this. So it concentrates around some value. Let's call it y0, and it has a variation. So typically, in general, this distribution will not be perfectly localized. So for the same feature values, we have different possible labels. And this is related, when you look at data, this is related to the fact that when you look at the scatter plot of the data, so you have some data points, then you have features of data points and labels. And when you do a cross section for a given feature value, then you typically have a spread here of data points that have very similar feature values, but different labels. And this width in the vertical direction corresponds to this posterior variance. And this variance is one way, or is one possible baseline. So if you come up with a probability distribution for features and label, then you can plug it into some scientific computing framework that can do this conditional distributions and read out the variance. And if the variance that you get out from here is, let's say, 0.1, then you know, okay, you are almost on the same level as the best method you can think of. And the best method you can think of uses the posterior distribution. There's no better way to do it. If you assume, if you subscribe to the probabilistic model. So if the data points are, for example, IID draws or realizations from this distribution, then the best you can do is this posterior variance. So this would be one way to get a baseline. Sounds good?
Yeah. So would I should I like create some kind of like a specific statistical model, this is just and then I can use that.
That's the problem. That's the problem. I mean, it's this whiteboard here is very patient. I can draw all these beautiful formulas and can write down these beautiful posterior distributions. But how do you get this probability distribution? Who tells you this?
Right.
For a game.
Right.
So one way to do it would be to collect many data points and fit a probabilistic model using maximum likelihood estimation.
Yeah. Okay. Hey, thank you. This sounds very good.
Sure.
Thanks very much.
Sure. Thanks a lot for this interesting machine learning application. Who wants to present next? Yeah, by the way, I just hit the record button. I will record the meeting always for my own purposes, and I will explicitly ask anybody contained in the recording for the consent if I want to post it somewhere, for example, on my YouTube channel. So don't worry, without your consent, this recording is only on my laptop.
Do you see it now?
Yes.
Yeah, so hi, my name is Thomas, and I'm also here for the first time. And I'm doing my bachelor's thesis on this like data set that Alex provided. It's from a factory, and I suppose it's like their air conditioning system or something.
Yes.
And the goal was to find dependencies between the different measured quantities, and these measured quantities are as timestamp data. And then when I found the dependencies, I would draw a kind of dependency graph based on it, and it could be used then to build like a graph neural network or something like that. And yes, I talked with you, Alex, last week, and I haven't had time to do the like any new results, but like I thought I would present to everybody else. The data has like nine different categories, or like quantities measured, and I've just to make it like more anonymous, I've just named them alphabetically, so that there wouldn't be like a bias from like knowing that some of the values are temperature or something like that. Then to analyze them, I've used like a time windows as the features. So I have used for like this one, I have used the A quantities a time window from the A quantity as a feature to model the B quantity. And the window size has been a bit different for the MLP regressor and the linear regression. So I think for this it was an hour, and for the linear regression it was 5 hours. And yeah, so and the results are like the red values mean that the model performs better than a just like average of the historical data. So and the blue models, they perform worse than just taking the average of the historical data. And then the number here indicates at like what time delta the first value in the window is. So for like almost every like working model, the best prediction was like taken at a time that was all or very closely proximate to like the predicted value. So we essentially, I think it was for like the H and I, they correlate very much with each other, but there is no use of knowing like the previous. So you can't predict in the future. You just predict by knowing what some of them are at this point. Yeah. So and then we concluded with Alex that this kind of approach might just analyze the temporalities in the data and not so much the dependencies between the different data, because like this H and I, if they are really similar values, then they just, there is not like these predictive, it's just like more of the yes, so more of the size differences in the values. So I think what I'll do next is like to try to fit a model based on just previous data of the same quantity. So just like a univariate time series analysis. And then I will add like the other quantity to see if it helps like this model. Does it become better or worse when it has any information from another like another quantity. So and my question is that how far should I want to like predict, because the data points are with 15-minute intervals, and from, I think this graph is the linear regression from like the age to the age, so it's or the ith to the ith, so it's this one, and yeah, clearly it's 0, because for like the time delta 0, but the error grows quite much already when you like take 5 hours back. So I wonder how long should it be, and yes, what should be the time delta when analyzing the like univariate case.
Okay, thanks a lot for the overview. So I don't know what the maximum time should be. I guess you see that it flattens out pretty quickly. Or no, this is the size of the window.
Yeah.
Yeah. I mean, this is one of the challenging things to find out, the horizon, how far you can predict into the future. In general, it is harder to predict further into the future.
Yes.
I mean, this is something you might then discuss with the PhD student who works on this from Germany. What they are interested in, how long into the future it is necessary or useful for them, because in the end they want to control a plant. So did you want to tell something else, Thomas, or can I now discuss a bit the setting?
No, you can discuss the setting, yes.
Okay, so in general, what Thomas is working on is you have a bunch of devices or sensors that generate data or time series. And this is a very generic model for almost any complex system. You can think of these nodes as neurons in the brain, and we measure their neuron activity. And the question then is often in understanding the systems, complex systems, is there an interaction? And in which direction? In which direction is the interaction? And one way to do this is to formulate this as a plain machine learning problem, a linear regression problem. So you would look at a pair. So you study pairs of time series and say, okay, at some fixed time, t0, so these need to be synchronized. You need to know the precise timing of this series. Otherwise, you cannot analyze the time series dependence, of course. You use this as the features, x, from one time series, and try to predict the future of this time series as the label. And then you basically shift, you have a sliding window. Then you get a new feature vector, and you get a new label, y2. And that's how you build up a data set for linear regression, for example. And as Thomas pointed out, it's typically not enough to say if we can predict the future from the past of this, but what we are actually interested in is, does this past help? Does the past of the other, let's say of node I, this is node I, help in predicting the future of node I prime beyond what we can do already with the past of node I prime? So we somehow want to cancel out or subtract from this analysis the intrinsic correlations of this time series at I prime. So we first try to predict the future of time series at I prime using the past at node I prime, and then we see, can we do better if we add the features from node I, if we add the past from node I? Does this help? Does this reduce the training error? And if yes, then we could say, okay, there might be a dependency in this direction. Node I might drive. So we could say node I drives node I prime.
How are you using, how are you evaluating the performance? Are you using some kind of information criteria or?
No, it's a training error. It's average squared loss, average squared error loss, for example.
Because a priori adding variables shouldn't decrease the loss, so decreasing the loss shouldn't, it's not necessarily an indicator that it's explaining something. If you add more variables, the error should not increase, right? So it's non-decreasing function. So
Yeah. But does it decrease significantly?
well, what's significant?
That's a good question. I would say maybe 10%, 20%. I don't know.
I think if you want to go in this direction, one way to look would be to go is to use information criteria. So like confirmation criteria, back basically the criteria that penalize for the number of additional variables. Because you actually want to see the intrinsic value of adding more variables, right? So if after penalizing for additional variables, your performance still improves, then probably there is added value in adding those variables. Versus if it does not improve, versus if the added value is balanced by the number of variables that you added, then maybe whether on the 10% or whatever number, it's not worth adding those variables.
Yeah, but does this approach not also involve some thresholds that you need to set to declaring, okay, this is now a significant improvement or not?
I don't think so. Let me double check. I mean, I think the basic scenario is that is where it essentially computes your training error, but it penalizes for the number of variables you used.
Yeah, but this you could take into account also by setting the required change in the loss. So if you add more other data sets or more other features, then you need to see more decrease in order to be significant. I mean, I don't see how this fundamentally solves the problem of setting such hyperparameters.
I wonder if it would be like valid to compare it to like a longer bit of or a larger bit of the like original times series or a larger window. So
yeah, the window size is also an important hyperparameter.
yeah, so if the window size there is like if we say it 10 there, and then you add 10 from the other time series,
yeah,
should it then be compared to a window size of 20 on the original? Because then the size of the features are the same and
yeah, I would start with varying this window size. Let's call this window size h, and then plotting the prediction or forecasting error as a function of the window size for a fixed lag into the future. So let's say we want to predict 2 time steps ahead. We fix this, but we vary age. And then at some point you might see that this flattens out. So beyond a certain window length, you do not get more information because it's like a more of a dynamic process. So it doesn't remember over longer periods of time. And I would say once you get into this floor, this is the age max, the maximum window length, and then you continue working with this.
yes.
Yeah, this is then this age max is what you use for comparing against the effect of adding the features from the other data from the other time series.
Yes.
Okay. And yeah, I mean, this is really a simple recipe for turning such a seemingly very difficult problem of estimating dependencies of a complex network into basic machine learning problems. And once you have done this, I mean, it's not too difficult then to change from linear models, so linear predictions, to nonlinear predictions. Then you can study, do you have nonlinear effects? So you would use, instead of the linear model here, a multi-layer perceptron to predict the label from the features.
Yes.
Okay, thanks a lot, Thomas, for the overview. I would say we continue, and if there are any additional questions or comments, please share on Slack.